Okay, so this is the section B of the second booklet of the 2018 end of year electronics exam. This section assesses criterion 7, which is a more mathematical section. Okay, so we have this resistor array like so. Show the resistor or the parallel combination is approximately 330 ohms. So R2 and R3 are the resistors in parallel. And so using the formula, it's going to be R1, so it's 1K. Actually, I'm going to write that as 1,000 because we're going to work in ohms on this one. And it's going to be 1 divided by that, which on my calculator is to the power of minus 1, plus 500 to the power of minus 1, all to the power of minus 1. Okay, and if I bring up my calculator, so 1,000 to the power of minus 1, plus 500 to the power of minus 1, close the brackets to the power of minus 1, now don't forget that last one, and you can see it's 333 ohms. Nearest whole ohm is fine for any resistance value you get. If the voltage at X is to be 7.5 volts, calculate the nearest E12 value for R1. Okay, so there's a lot in this part. So looking at the voltage divider formula, so V out is V in times the resistance, and this is going to be this 330 ohms resistance. So let's just use the formula. So R2 over R1. What's going on? Plus R2. So the output is the input times the so R2 would be the equivalent resistance of this lot, and R1 plus R2 is the equivalent series resistance between the 12 volt power supply there. So we can put in some numbers that we know and try and find out some stuff. So we know the output is 7.5 volts, the input is 12. R2, we're going to use our 333. We don't know R1. Okay. So rearranging this a little bit, I find the easiest way is to get this unknown one on the numerator there, and the best way to do that is sort of flip all of the equations. So I'm going to multiply everything on this side by that, and sort of go away. So I'm going to combine that into sort of two steps here. So we get R1 plus 333 over 333 is going to be 12 divided by 7.5. Okay. So now if I multiply both sides by 333 and then subtract 333 from it, I get R1 is 12 over 7.5 times 333, subtract 333. And using my calculator, I can do that. So 12 divided by 7.5, and then times 333 minus 333. Now, just got to check to make sure it's done it the right way. That looks about right. So what I would expect here is that this output voltage is a bit over half of the input voltage. So the 333 ohms is going to be a bit over half of the total resistance, which is about 533 ohms. So this is 199.8. Well, let's just narrow it to the nearest whole ohm, so 200 ohms. So the nearest E12 to that, it's either going to be 180 ohms or are 220 ohms, and they're both about the same distance, so let's choose 180 ohms. Okay. But you could have chosen the 220 ohm resistor either. So both of those are equally distant apart from the 200 ohms, so it doesn't really matter. Okay, we haven't looked at this stuff yet. This is all about impedance, so skip over that one. Okay, question 24 is a pickaxe microcontroller type question, and as you can see, this is all about writing some code. Okay, so we've got some code there. Before I start trying to analyse the code too much, probably pays to read the question, because you can analyse the code and then not be asked anything about that. Okay, so in the spaces provided on the previous page, explain in detail the role of lines 1 to 7. So we're actually going to have to sort of look at the code. Alright, so here we're setting some symbols here. So we've got LED equals 4, so connect, or LED is on pin 4. So LED connected to pin 4. And we've also got a switch that looks like it's on pin 2. So switch connected to pin 2. Okay, you'll notice here that we've just got a number on LED there. So when you set an output, you just refer to it by its number. But if you've got an input, you have to call it pin something. Okay, so this looks like it's checking. So if PB switch is equal to 0 or 1, then we do these different things. So we're going to check the switch. The PB switch would be a push button switch. So check the switch condition. Okay, so is it pressed or not? That's kind of what that's doing. Okay, so flash, we'll let B2 equals 5. For counter equals 1 to B2, we're going to high the LED, pause it, then low the LED, and then pause it, and then we're going to increment the counter by 1. That's what next counter would do. So this is going to flash. So this is 5 flashes. So this is how many times it's going to do this little cycle. So this for loop here is going to be repeated 5 times. So 5 flashes of LED. And here this determines so this pause 500 is going to set the frequency to 1 divided by the sum of these, which is 1000 milliseconds, so 1 over 1, so 1 hertz. Okay, so that's what that part's going to do. If you said set delay for on and off, of the LED, that would also be a sort of a reasonably accepted answer. And here you can see when it's finished this, it's going to have a bit of a wait, so it's going to wait 2 seconds and then loop back to this main. So loop back to the switch checking. Loop. Okay. Okay. So flash 1 is a different subroutine here. So here we've got let B2 equals 15 and counter equals 1 to B2. So this is going to flash LED at, notice that the time here is now half of what it was before, so the frequency is going to be now 2 hertz, and it's going to count it 15 times. Okay, so it's going to flash the LED twice a second, 15 times. And then it's going to go back to the main again when it's done. Okay, part B. The pickaxe microcontroller that contains the above program is connected to an appropriate circuit and tested. Describe in detail the operation of the circuit. Okay, so the notice that there's a wait 2 after each at the end of each subroutine there, and the switch can only be in one of 2 different conditions. So it's going to do this one or this one. So it's either going to flash 5 pulses. The circuit will either flash 5 times at 1 Hertz or 15 times at 2 Hertz, depending on the switch. Position. I'm not sure what else they're after there. There seems to be not a lot for 3-mark question, but I suppose in order to write all that down, you had to fully understand the code. Okay, another op-amp question, so we're not going to look at that. Another amplifier question, so we're not going to look at that. Okay, digital circuit question. Okay, so a student constructed this circuit and developing a new traffic light system. So IC1 is a 7-bit binary ripple counter. Okay, so the outputs Q4 to Q6 are labelled A, B and C, and they're connected to some logic gates here. Complete the R, Y and G, so that would be R, Y and G there would be my outputs. Okay, so here what we're going to do is we're just going to look at what inputs are connected to each one, and extrapolate from this. So you can see that the R is only connected to Q6, and it's by an inverter here. So whatever is on R is going to be the opposite of whatever is on Q6. So Q6, when it's 0, the output's going to be 1. So these are all going to be 1s, and these are all going to be 0s. And that last one's going to be 1. It's probably easier to ignore Y for the second. Let's look at G here. G is directly onto Q6, so you can see that's just directly connected. So G and Q6 are going to be exactly the same. So just copying those across. So I'm just looking at that column there for only looking at that. When we're looking for finding R and G. Okay, so I didn't even need to consider the other logic circuits and the outputs from Q5 and Q4 to work out what R and G do. Okay, so Y is the ANDed output of Q5 and the output of Q4 ORed with Q6. So here, this is an AND gate, so if the only time the output Y can be 1 is when both of these inputs are 1. So if this input here, which is connected to Q5 or B, is a 0, the output Y must be a 0. So we can look at those. So that's a 0. They're both going to be 0. And this one's going to be a 0. Okay, now if this one is a 1, this one also needs to be a 1. So the only time that these are going to be 1 is if either 4 or 6 is 1. So 4 or 6 is a 1 and B is a 1, then we get a 1. So B is a 1 there. So B has to be 1, but both either one of 4 or 6 have to be 1. But if it's not, so here, looking at this one, they're both 0. So Q4 and Q6 are both a 0. So the output of the OR gate there is going to be 0. So this output will be a 0 as well. Just looking at the gaps here, we've got a 1 here. So the output of the OR gate is going to be a 1. And B is a 1. So that's going to be a 1. Okay. So I suppose the strategy here was, let's fill out all of the things that we can do really easily. So for example, R was quite easy. It's just relied on one input. G was easy. It just relied on one input. With the Y, so we left Y last, I looked at the ones where I know what the output will be based on only one input. So if this output B, or Q5, was 0, then Y had to be a 0. That was the only way it could be. And so I was able to sort of fill out those, and then that left just a few left to do that were a little bit more involved. And so that's an easier way. Okay, describe how the operation of the yellow and green lights are controlled by A, B and C. Okay. Okay, so the green is always opposite of red. Okay. Okay, so that's effectively what's happening here with this inverter here. It makes it so that green and red can't both be at the same state, which, you don't want that. And the yellow is going to be shown for a short time before it turns back to red again. So yellow is shown for a short time between changes. Not really quite sure what else it asked for, was requiring there. So I think that it's really just, how do you interpret what you see. Okay, so this will be a basic principles type question. So we've got a high power infrared LED, and this would be like a section out of its data sheet. Okay, so we've got a few characteristics here. So physical characteristics, color of the lens, some electrical characteristics, so voltage, current, power, or peak current, reverse voltage, its intensity, so how bright it would be, a particular current, and its frequency of light, so its colour. And okay, so what would be the voltage drop across the LED when it's glowing? I can just read that straight off. This is this forward voltage drop there, so it's going to be 1.5 volts. And what is the maximum continuous power dissipation of the LED? So this is the max constant forward current at 100 milliamps. Okay. So we would use so power is the voltage times the current. So we would use this 1.5 volts times the current of 100 milliamps, which is 0.1 amps, which is going to be equal to 0.15 watts, which is, in a better unit, would be 150 milliwatts. Calculate the minimum E12 value of the required dropping resistor for steady current flow. Okay, so we need to use, based on this 100 milliamps current, and we're going to have a voltage drop of 1.5 volts. So the voltage across that resistor, the voltage is going to be 18 minus 1.5 volts. Don't forget to subtract the forward voltage drop of the diode, because we're just looking at the resistor value. And so it's the voltage across the resistor and the current of 100 milliamps. So this is going to be 16.5 volts and 100 milliamps. So R is V over I. So that's 16.5 divided by 0.1, which is 165 ohms. Now you can't get a 165 ohm E12 resistor. You got 160 and 180, 150 and 180. So if I would choose the 150, that would give me more than 100 milliamps of current, so I have to choose the next size up. So therefore E12 equals 180 ohms. And that'll keep the current below 100 milliamps. And well, the fact that we're not even close to 180 on our calculation here means we don't need to worry about calculating what the tolerance would need to be, or whether a 5% tolerance would be suitable. Find the power dissipated. So this is going to be at this is going to have, so the voltage, I'm not going to try and calculate the current because I have to recalculate everything with that, but the voltage is going to stay at about 1.5 volts across the LED, so the voltage is going to stay at 16.5 volts, and R is 180 ohms, so P equals V squared on R would be the easier way to calculate that. So 16.5 squared divided by 180 equals is 1.51 watts. That's a fair bit of current, a fair bit of power. Did I do that right? Well, I suppose 16.5 squared is a fairly big number, so yeah. Okay. Question 29 looks like a number conversion one. So we're going to convert 4e in hexadecimal, so base 16, to decimal. Now my preference is always to convert from hex to binary and then binary to decimal. So 4e in binary is going to be 0100, and e is 1 less than f, so it's going to be 1110. So this is the binary number, and now this is my 1s, 2s, 4s, 8s, 16s, 32s, and 64s, and well 128s. So it's going to be 64 plus 8 plus 4 plus 2 equals, so 74, 78. That's in decimal. So right, binary, base 10 there. Okay, part B, converting to BCD. So this is a decimal number, and we're converting it to BCD, which is binary coded decimal. So we just convert each digit to a 4-bit binary number. So 7 is 0111, 5 is 0101, and 4 is 0100. And so BCD is going to be 0111, 0101, 0100. Okay. I've just put a little space there just to make it a bit easier to read. I would recommend that you do that with your maybe groups of 4 bits. If you're working with octal, groups of 3 bits is also useful too. Okay, so binary, add these two binary numbers together and then convert it to octal. So to add the numbers, I'm going to set it up like this: 1001, 1011, and directly below that because trying to line up the bits. And we're adding them. And just like when you're adding in long addition, 1 plus a 0 is a 1. 1 plus a 1 is a 2, which is 0 carry the 2. 1 plus a 1 is a 2, which is 0 carry the 2. 1 plus a 1 plus a 1 is a 3, which is a 1 carry the 2. 1 plus a 1 is a, 1 carry the 2. That's going to be 1, no carry, 1, no carry, and 1, no carry. So this is the binary, the sum in binary. Now in octal, we group them up in 3s. So that's going to be a 1, that's going to be a 7, and that's going to be a 4. It's not 4, that's a 3. So the sum of these is 371 in octal. So question 30, been asked to fit an alarm to a portable cooler. Sound the alarm if the danger of the contents not being kept cold enough. So we've got some sensors. So F is if there's food in there, 1 if there's food, T if the temperature is too high, C is 1 if the lid is closed, and P is 1 if the power is on. The alarm is a sound when A is 1. This occurs when at least one of the following occurs. So if the power's off, or the temperature is too high, or the temperature is low but the lid is open. Okay, so we've got P equals 1 is the temperature being, the power being on. So we want not power, right? So A is our answer. This is going to be true when the not power or temperature is too high. So there's a T there, so P or T, or if the temperature is low, so this would be not T, and the lid is open, so C is 1 if the lid is closed, so it's not C as well. Okay, and I don't think we can simplify that any further, and we probably shouldn't try. So the alarm will sound, A is 1, when it's or, so any one of these or more, the power is off, the temperature is too high, or the temperature is low, but also the lid is not closed. Okay, so using this Boolean expression, we've got P, T, and C. So not P gives us this one, T gives us that one, and not C gives us that one, and not T gives us that one, and they are ANDed together there and ORed together. Now I'm going to use two input OR gates. So that's an OR gate there. Now if you just cascade them together like this, it works. Because if only one of these is true, then if only one of these ones is true, then that'll be true, which will also make this true. Okay. And this is my output A. And I think that's the end of section B.